Welcome to solution concentration in mass percent. So in chemistry, the concentration of a solution is usually expressed as molarity, but it can also be expressed in other ways. And one of these ways is mass percent. Now mass percent, or percent by mass, is the mass of the part, the solute, divided by the mass of the whole, that entire solution, multiplied by 100%. For example, in a 5% by mass sodium chloride solution, 5 grams of sodium chloride are contained in 100 grams of solution. Now note here that this is 100 grams of solution, not 100 grams of water. If we have 5 grams of sodium chloride, then in that 100 grams of solution, we have 95 grams of water. So to help with our calculations, we can define mass percent in one of 3 ways. Mass percent is equal to grams of solute dissolved divided by total grams of solution times 100%, or X percent by mass means X grams of solute per 100 grams of solution, or X percent by mass means the decimal equivalent, grams of solute per 1 gram of solution. Now, note that our first definition is simply that mass fraction multiplied by 100%, and that first definition is useful if the wanted is a mass percent. If the mass percent is in the data, then use the second or third definition. Now, note that all 3 of these definitions are mathematically equivalent, so you can, in principle, use any of the 3, but one definition may be easier to use than another. So we can solve mass percent problems using conversions, and some specific rules to use are: if a mass percent is wanted, solve for the mass fraction first, as we do here. So we want percent mass, so solve for grams of solute divided by grams of solution, and then convert that mass fraction to the decimal equivalent, and then convert to mass percent. If a percent by mass is supplied as data, then write in your data section, X percent by mass means X grams solute equals 100 grams of solution. And note that you could use the third definition here instead of the second if you choose to, in which case you have X percent by mass means the decimal equivalent, grams of the solute equals 1 gram of solution. So label each number and unit as measuring either the solute or the solution, and if the moles of the substance are mentioned in the wanted or data, write its molar mass in the data. If the moles of a substance is not mentioned, then you will not need the molar mass. Bear in mind that there is nothing wrong with writing that molar mass equality in that data section, you just won't necessarily need it to solve the problem. In chemistry, if a concentration is expressed as a percent, but it is not identified as a mass percent or a volume percent, then assume that it is a mass percent. For example, if 3% HCl is given as data, then write 3 grams of HCl is equal to 100 grams of solution. So we can now use these rules to solve mass percent calculations. For example, if the density of a 3.31 molar KOH solution, so this is potassium hydroxide, is 1.14 grams per milliliter, what is its percentage concentration? First, we want to write the wanted. So the wanted is a percent concentration, and that means that that is the mass percent, or the percent by mass. Next, let's write the data. We know 3.31 moles of potassium hydroxide are equal to 1 liter of solution of potassium hydroxide. We know that 1.14 grams of solution are equal to 1 milliliter of solution. We know that 1 mole of potassium hydroxide is equal to 56.1 grams of potassium hydroxide from the molar mass of potassium hydroxide. And now a mass percent is wanted, so we need to solve for the mass fraction first. And we want a ratio. Remember, a fraction is simply a ratio. So we need to start with a ratio. So we already have our wanted and data sections, and now in our solve section, we want that mass fraction. So we want grams of potassium hydroxide divided by grams of solution. So let's start out with a unit that we have. We want grams of potassium hydroxide in the numerator. So let's start out with grams of potassium hydroxide from here, from our molar mass, and then we need to put 1 mole of potassium hydroxide in the denominator. And now we need to get rid of 1 mole of potassium hydroxide, so our moles of potassium hydroxide there and moles of potassium hydroxide here from our concentration will cancel. And now we need to put 1 liter of solution in the denominator. So now we have grams of potassium hydroxide divided by liters of solution. But we don't want liters of solution, we want grams of solution. So now we need to convert from liters of solution to milliliters of solution. So liters of solution goes away, now we have milliliters of solution. And then we want to get rid of milliliters of solution and convert to grams of solution from our density here, 1.14 grams of solution equal 1 milliliter of solution. And when we work out the math, it equals 0.163 grams of potassium hydroxide divided by grams of solution. So 0.163 grams of potassium hydroxide per gram of solution. And now we can convert from our decimal equivalent of the mass fraction to the percentage. So 0.163 times 100% equals 16.3% potassium hydroxide by mass. Now, a dilute solution is generally one in which the solute concentration is less than 0.2 molar or less than 1%. Now, when calculating using percent concentrations, we often need to know the density of the solution. Now, a dilute solution is at least 99% water by mass because it can't be more than 1% of our solute. And this means that we can add the following approximation to our rules for percent concentration calculations. In a percent concentration calculation about a dilute aqueous solution, if no density is applied, then write in your data 1 milliliter of dilute solution is approximately equal to 1.00 milliliters of water, which is approximately equal to 1.00 grams of water, which is approximately equal to 1.00 grams of solution. And now we have a way of getting from volume of solution, milliliters of solution, to mass of solution, grams of solution. In a solution that is not dilute, if it's more concentrated, then that mass of the solute becomes significant and that above approximation fails. So in higher concentration solutions, this is any solution that isn't dilute, so any solution where the concentration is higher than 0.2 molar or 1%, the total mass of solution is equal to the mass of the solute plus the mass of the solvent. And we need to attach labels that distinguish the solute, the solvent, and the solution from each other. For example, in 100 grams of 14% potassium chloride, what is the mass of potassium chloride in the solution? And what is the mass of water in the solution? Well, the mass of potassium chloride is 14% of 100 grams. This should be a lowercase g here. And that is 0.14 times 100 grams. Again, this should be a lowercase g. And that equals 14 grams. The mass of water is the remainder of the mass of the entire solution. The entire solution was 100 grams. We have 14 grams of potassium chloride, and that means we have 86 grams of water. Now, in health science fields, the concentration of solutions is often expressed in different terms than in chemistry. One of the terms that they use is percent by weight, or percent weight weight, or percent W/W. This all means the same thing. This is all a percent by weight. And this has the same meaning as mass percent. Because while weight and mass are not the same thing, in constant gravity, in other words, on Earth's surface at a constant height, so within some room, they are proportional, and thus they can be measured with the same instruments. Another term that you may see is percent weight by volume, which is sometimes abbreviated percent W/V. And this is defined as percent weight by volume is equal to mass of solute divided by volume of solution, so grams of solute divided by milliliters of solution, times 100%, or as X grams of solute per 100 milliliters of solution. And so the assumption here is that your density for solution is approximately 1.0 gram per milliliter, and that means that you have mass of solute divided by mass of solution, because as long as you have a dilute solution, that approximation holds. So let's add rules for percent weight by weight and percent weight by volume to our rules for percent concentration. So unless otherwise specified, assume the unit of mass and weight is grams and the unit of volume is milliliters. If a problem expresses solution concentration as a percentage weight by weight, or percent W/W, or percent by weight, then assume weight really means mass, and use the mass percent rules that we've already discussed to solve it. If, on the other hand, a percent weight by volume is wanted, then solve for the fraction first. That is, find percent weight by volume is equal to grams of solute divided by milliliters of solution, and then convert to the decimal equivalent, and then convert to percentage. And if any X percent concentration is given, then write in your data X percent means X units of solute equals 100 units of solution. Now you should replace units here with whatever units you're using to measure. So if it's mass, then grams of solute and grams of solution. And you should actually specify what the solute is. Don't just write out the word solute. Write the chemical formula of the solute, so sodium chloride or potassium hydroxide, whatever it happens to be. And in dilute solutions, the mass percent is equal to percent weight by weight, and is also equal to percent weight by volume. And this is because dilute solutions have a density of approximately 1.0 gram per milliliter, so that volume in milliliters is approximately the same value as the mass in grams. And that was solution concentration in mass percent.